Imagine a cannonball fired high into the air. We can use classical mechanics, the physics developed by Isaac Newton, to accurately predict the path of this cannonball. We can determine its trajectory, its velocity, and even how long it will take to reach its target. Classical mechanics deals with the macroscopic world, the world of everyday objects we can see and touch. It's based on the idea that objects have definite properties, like position and momentum, which we can measure with certainty. If we know the initial conditions of an object, like the cannonball's angle and speed upon firing, we can predict its future with remarkable accuracy. This predictability is a cornerstone of classical mechanics. It's what allows us to design bridges that stand firm, predict the motion of planets, and even send rockets into space. The laws of classical mechanics are deterministic, meaning that the present state of a system completely determines its future. There's no ambiguity, no randomness, and everything unfolds according to a precise set of rules. This predictability, however, breaks down when we enter the microscopic world, the realm of atoms and particles. Here, a new set of rules govern, the enigmatic laws of quantum mechanics. In the early 20th century, physicists made a startling discovery. The laws governing the microscopic world were fundamentally different from those of the macroscopic world. This led to the development of quantum mechanics, a revolutionary theory that has profoundly changed our understanding of the universe. Unlike classical mechanics, quantum mechanics is not deterministic. Instead, it's based on probabilities. We can't say for certain where a particle is or how fast it's moving. Instead, we have to talk about the probability of finding it in a particular location or with a particular momentum. This inherent uncertainty is not due to a lack of knowledge or limitations in our measuring devices. It's an intrinsic feature of the quantum world. Particles don't have definite properties until they are measured. Before measurement, they exist in a superposition of states, a concept we'll explore further with Schrödinger's cat. This shift from certainty to probability was a radical departure from classical physics. It introduced an element of randomness and uncertainty into our understanding of the universe, challenging our intuitive grasp of reality. To illustrate the strangeness of quantum mechanics, let's delve into a famous thought experiment, Schrödinger's cat. Erwin Schrödinger, one of the pioneers of quantum mechanics, devised a thought experiment to highlight the paradoxical nature of quantum superposition. Imagine a cat placed inside a sealed box. Inside the box, there's a radioactive atom, a Geiger counter, and a flask of poison. Here's how the experiment works. If the radioactive atom decays, the Geiger counter detects the radiation and triggers a mechanism that releases the poison, killing the cat. If the atom doesn't decay, nothing happens, and the cat remains alive. According to quantum mechanics, the radioactive atom exists in a superposition of states, both decayed and undecayed, until it's measured. This means the cat is also in a superposition of states, both alive and dead, until we open the box and observe its state. This thought experiment highlights the bizarre implications of quantum superposition. It suggests that the act of observation somehow forces the system, the cat, to collapse into a definite state. Until then, it exists in a limbo of possibilities, both alive and dead. Schrödinger's cat is a thought experiment, not a real experiment. It's meant to illustrate the strangeness of quantum superposition and the challenges it poses to our understanding of reality. Superposition is a fundamental concept in quantum mechanics. It means a quantum system, like an electron or an atom, can exist in multiple states simultaneously until it's measured. Think of a coin spinning in the air. Until it lands, it's neither heads nor tails, but a blur of both possibilities. Similarly, a quantum particle in a superposition is in a blend of all possible states. It's not that we don't know which state it's in, it's that it's genuinely in all states at once. This is a radical departure from our everyday experience. In the macroscopic world, objects have definite properties. A light switch is either on or off, a door is either open or closed. But in the quantum world, things are fuzzier. The act of measurement disrupts this superposition, causing the quantum system to collapse into one definite state. This is what happens when we open the box in Schrödinger's cat experiment. The act of observing forces the cat to be either alive or dead. Superposition is one of the most counterintuitive aspects of quantum mechanics. It has profound implications for our understanding of reality, suggesting that the act of observation plays a fundamental role in shaping the universe. Section 5. Entanglement, spooky action at a distance. Entanglement is another bizarre phenomenon in quantum mechanics that has no classical counterpart. Imagine, if you will, two particles that are entangled. This means their fates are intertwined, no matter how far apart they are. If we measure the state of one particle, we instantly know the state of the other particle, even if they are light years away. This connection between entangled particles is instantaneous, seemingly violating the speed of light. Einstein famously called this spooky action at a distance because it seemed to contradict his theory of relativity, which states that nothing can travel faster than light. Entanglement has profound implications for our understanding of space and time. It suggests that there's a deeper level of connection between objects in the universe than we previously thought. Entanglement is a real phenomenon that has been experimentally verified. It's one of the most intriguing aspects of quantum mechanics, with potential applications in quantum computing and communication. Section 6. The measurement problem. Collapsing the wave function. The measurement problem is one of the most fundamental and unresolved problems in quantum mechanics. It arises from the clash between the deterministic evolution of the wave function, which describes the state of a quantum system, and the seemingly random collapse of the wave function upon measurement. According to quantum mechanics, the wave function evolves smoothly and continuously, governed by Schrödinger's equation. This evolution is deterministic, meaning that the present state of the wave function completely determines its future state. However, when we measure a quantum system, the wave function seems to instantaneously collapse into one of its possible states. This collapse is random, meaning that we can't predict with certainty which state the system will collapse into. The measurement problem is essentially, how does the act of measurement cause the wave function to collapse? What constitutes a measurement? Does it require a conscious observer, or does it happen even without one? These are questions that have puzzled physicists for decades. There are various interpretations of quantum mechanics that attempt to address the measurement problem, each with its own strengths and weaknesses. One of these interpretations is the many worlds interpretation. Section 7. Many worlds, a mind-bending solution. The many worlds interpretation, or MWI, offers a radical but elegant solution to the measurement problem. It suggests that every time a measurement is made, the universe splits into multiple branches, each representing a different outcome of the measurement. In the context of Schrödinger's cat, this means that when we open the box, the universe splits into two branches. In one branch, the cat is alive, and in the other, the cat is dead. We, as observers, only experience one of these branches, but in the other branches, all other possibilities continue to exist. This interpretation eliminates the need for wave function collapse. Instead of the wave function collapsing into a single state, it continues to evolve, encompassing all possible outcomes in different branches of the universe. The MWI is a deterministic interpretation of quantum mechanics. The evolution of the wave function is completely determined by Schrödinger's equation. The apparent randomness of quantum measurements arises from the fact that we are only aware of one branch of the multiverse. While the MWI is a mind-bending concept, it offers a consistent and elegant solution to the measurement problem. It's a testament to the profound strangeness of quantum mechanics and the challenges it poses to our understanding of reality. Section 8. The Quantum Frontier, Unanswered Questions and Future Explorations. Quantum mechanics has revolutionized our understanding of the universe, but it has also raised many profound and unanswered questions. What is the nature of wave function collapse? Is the many worlds interpretation correct? Or is there another explanation for the measurement problem? What are the implications of quantum mechanics for our understanding of consciousness and free will? These are just a few of the mysteries that lie at the forefront of quantum research. As we delve deeper into the quantum realm, we are likely to encounter even more strange and counterintuitive phenomena that challenge our fundamental assumptions about the nature of reality. The field of quantum information science is rapidly advancing, with potential applications in quantum computing, communication, and cryptography. Quantum computers, for example, could potentially solve problems that are intractable for classical computers, revolutionizing fields like medicine, material science, and artificial intelligence. The future of quantum mechanics is filled with both promise and uncertainty. As we continue to explore the quantum frontier, we are likely to make groundbreaking discoveries that will transform our understanding of the universe and our place within it. Section 9. Conclusion. Embracing the enigma of the quantum world. The quantum world is a strange and wonderful place, full of counterintuitive phenomena that challenge our everyday experience. From superposition and entanglement to the measurement problem and the many worlds interpretation, quantum mechanics has forced us to confront the limits of our classical intuition and embrace a new understanding of reality. As we continue to explore the quantum realm, we are likely to encounter even more mysteries and wonders. But one thing is certain: the journey into the quantum world is a journey into the very heart of reality, a journey that is both exhilarating and profoundly humbling. So the next time you look at a cannonball soaring through the air, remember that beneath its predictable trajectory lies a hidden world of quantum strangeness, a world where particles exist in multiple states at once, where entanglement connects distant objects, and where the very act of observation shapes the fabric of reality. What other mind-boggling secrets does the quantum world hold? The answer, my friends, is out there, waiting to be discovered.